Okay, so I think we can resume for our second talk of this morning. And it's my pleasure to have Sara Murciano talking about observable-projected ensemble. Thank you.
Thanks, Veronica, and thanks for the opportunity of being here. Today I will talk about a recent work that I've been doing with Alexei Milekin, who is a postdoc in Caltech. And it's about, since the topic of the SIP seminar was about probability theory, statistical mechanics, this work is about a distribution of states that I will call projected ensemble or observable projected ensembles. So let me first give some motivations on, let's say, how this idea was born. And okay. The idea arises in the context of measurements in many-body quantum systems. So what does it mean? So far, if you think about measurements, now when I do a measurement, usually it's a way to probe quantum matter, like to understand some properties of the state, something like this. But recently, people have tried to use a different perspective on how to use measurements to, for instance, generate novel quantum phenomena. And one of the main topics that in this setting of generating novel quantum phenomena was studied is what is called an entanglement phase transition. What does it mean? So suppose that you have a system and you let it evolve. So the unitary dynamics, usually what this does is to increase the entanglement of the system, because eventually you will reach the thermodynamic entropy where the entanglement scales extensively as a function of the system size. So we have an entanglement growth. On the other hand, you can intuitively think that if you project your system during these dynamics, making a projection means killing the entanglement of the system. Eventually, if you do a full projection of a given wave function, you will project it into a product state. So the entanglement, as speaking, vanishes. And so we have a kind of competition between an entanglement growth due to the unitary dynamics and an entanglement saturation due to the fact that we perform measurements in our dynamics. And people have found a transition in the entanglement behavior depending on the frequency with which these measurements are performed during this dynamic. And at this point, the entanglement, for instance, can grow logarithmically as a function of the subsystem size. And this reminds the behavior of the entanglement entropy in critical systems. So this phenomenon has been studied a lot here. I just report the first, it's a very small subset of references about the topic. Okay, so I said that entanglement can create novel quantum phenomena out of equilibrium. But actually something that I've also been studying recently is the impact of measurements just in the ground state of critical systems. So you have a system which is critical, and we know that critical systems are characterized by specific properties. Like if I think in terms of the behavior of a correlation function or of the behavior of the entanglement, these are very constrained by the specific critical theory that I'm studied, so by the so-called universality class of the theory that I'm studying. And this is rigid. Like if I look at the decay of some supercorrelation function, the decay that it has is fixed by the criticality, by the kind of critical theory that we are studying. And so the question is how this rigid behavior of critical systems is affected by measurements. Like if you perform measurements in the ground set of critical system, what happens? And yeah, this is something that I'm currently working on. So in case later you want to discuss about this, I'm very happy. And another let's say overlap between measurements and interesting phenomena that I really like is the possibility of using measurements in order to prepare interesting states it's written long-range correlated state. What does it mean? It means that the idea is simple. So rather than preparing a state by performing some time evolution or by tuning your interactions in a specific way, one wants to start from a state and then do measurements on this state in order to create a different state. And here I want to give you a very short and I think nice example, which was described in this work done in the group by Viswanathan. And the example is the following. So you start from a very simple state, like a product state in the X basis. Then you apply a set of unitary gates that create an Hamiltonian, which is called cluster Hamiltonian. And as you can see, this cluster Hamiltonian is characterized by a three-spin interaction that I call here ZXZ. And if you think in terms of the correlation function or the expectation value of this three-body interaction in the ground state of this Hamiltonian, this is just equal to 1. And then I perform measurement on these red dots, so on the even sides in the X basis. And this is denoted by this plus, minus, minus, plus, minus, minus. This is the measurement outcome that I get. And then I flip the spins on the odd sides based on the measurement outcome that I get on the even sides. So in this way, I created a GHZ state that maybe in a very rough way, you can somehow think that if I have an Hamiltonian with interaction ZXZ and I project X into a specific measurement outcome, 1, I get a ZZ Hamiltonian whose ground state is indeed the GHZ state. So this is a very intuitive and rough way, let's say, to understand what we are doing. So this is, I think, very nice, because at the end we're starting from a state, the cluster state that has 0 correlation. If you compute the correlation function of the ZZ operators, these are 0, but then you get a GHZ state that we know if you compute the two-point correlation function of the Z operator, you get something which is order 1. I've given 3 examples in which we have used measurements to find interesting features ranging from entanglement transition to state preparation. So in this context of, let's say, performing measurements on many-body quantum system, we can start talking about projected ensembles. So ensembles of states that we generate once we perform measurements, not on the full system, but just on part of the system. So I perform measurement on part of the system and I get an ensemble of states, which are called projected ensembles. And they will be the main topic of this talk. So I will first introduce the idea of projected ensembles, also here trying to explain why they were introduced and what are the main properties. Then I will focus, my question was to try to understand these projected ensembles more in a field theory setup. Try to study these projected ensembles from, for instance, for critical systems. A spoiler, we didn't manage to address directly this question, so we introduced a different kind of ensembles that we call observable-projected ensembles, that is more amenable for field theoretical computations. I will provide some example of the computations that we did, and finally I will draw some conclusions. And feel free to interrupt me at any point if you have questions. Okay, so we said projected ensembles, why people started looking at these projected ensemble. Now, the motivation comes from, let's say, the experimental community working between condensed matter and quantum info, where how modern quantum experiments are done. Basically, they have a system, they have some spins, for instance, and then they take some snapshot by measuring in a specific basis, like for instance, the occupation number basis. And they do it several times, such that they collect a lot of snapshots, not describing their system. So here I denote a set of strings, Z, which contains the measurement outcome that they read at any site. What can I do now that I have all this data? Well, for instance, I can try to reconstruct the one-point correlation function. And how should I do? I will just take, for instance, if I'm interested in the one-point correlation function on the second site, I sum over all the entries, the second entries in my string, and I average overall the measurement outcome that I denote as M. Okay, so in this way I can compute the one-point correlation function. Similarly, if I want to compute the two-point correlation function, no, I just sum over the entry on the second and on the ninth site. But
It's just an average, no?
it's just an average, yes.
So these states, each measurement you need to re-prepare your
Exactly, you have to reload your atoms and
prepare the state again. Prepare
yes.
the initial state again. I see.
Yeah, for them it's just a reloading. Like indeed, they usually use simple states where this can be done efficiently. Yes, and then this is why, I mean, any measure, it's any outcome is different with respect to what you get before. Like they are independent one from each other. But when I compute these local observables, there is a problem because, I mean, somehow we are neglecting all the information that is encoded in the rest part of the system. So the question is there a way to keep track of this information? Is there, let's say, a smarter way to, for instance, compute some expectation value, but keeping track of the information that we have in the full system without throwing away all the information which is encoded in the rest of the system? And the basic idea is that I can compute the expectation value of an observable on a given region, A, but condition on the fact that we get a specific measurement outcome in B. So for instance, it means that I constrain my expectation value on the second site just if the remaining site have a specific pattern, and then I throw away all the rest. In this way, when I compute an expectation value, I keep track of the information of what we have measured also in B. No? This is the main idea. And indeed, what in these two papers has been done, both from a theory point of view and also this Nature paper is an experimental work, is to study, is to define this concept of a projective ensemble as follows. So you have a wave function, psi, you can think as a bunch of spins. You split it into two parts, A and B, and then you measure B in a given basis, like Z basis in this case. And as a result of this operation, I get a wave function psi, which is a tensor product between two pure states, one which is the measurement outcome in B, and the other one which is the post-measurement wave function in A, but now conditioned on the fact that we got a specific measurement outcome in B. Okay, so let's define this psi A of ZB. Given this expression for the projector in ZB, notice that this is just the tensor product between the identity in A, because A is untouched, we haven't done anything. So we have the identity in A, tensor product a projector in B, and this defines the probability of getting ZB as an outcome of my measurement. And then the post-measurement wave function in A is just given by an overall normalization factor. Then again, the identity in A, tensor product ZB acting on the original state. So this state is a pure state living in the Hilbert space of A. Okay. And if we collect all the probability distribution P of ZB and the post-measurement wave function, so these pure quantum states, we create this projected ensemble. So this is the definition of the projected ensemble. I have a system, I measure just part of the system in B, and then I get a post-measurement wave function subject to a specific measurement outcome in B. And at this point, one can ask, okay, what are the properties of this projected ensemble? So yeah, first of all, let me stress the projected ensemble is creating a distribution of pure states over the Hilbert space of A. And what are the properties of this pure state? Well, in order to compute them, what we have to do is compute the moments of this distribution of pure states. So I sum overall my measurement outcome, the first moment, which is simply the density matrix in the subsystem A, constructed by my original state. But if I plug the definition of the post-measurement wave function and I sum over all the measurement outcome, this first moment can be simply rewritten as this trace over B of psi psi. And this is called reduced density matrix because it means that we are performing a trace not over the Hilbert space, which is given by A and B, but only on B. So this is the reduced density matrix. So the first moment is a bit trivial, let's say, no? Because we are just getting the reduced density matrix. There is no information about what the measurement that we did. What happens if we look at the higher moments? Indeed, these higher moments are much less trivial to compute, and these are it's the higher moments that contain, let's say, the interesting information about the possible distribution of states that we can get by performing this measurement. And a setup in which these higher moments have been computed and have revealed interesting physics is again out of equilibrium. So what was the setup? Suppose that I have a state, psi naught, I let it evolve with a given Hamiltonian, and I get an evolved state that I call psi of t. Now I can focus on a subsystem A because we know that if the evolution is unitary, the system doesn't thermalize because it remains as it is. If I'm interested in, let's say, if I'm interested in the concept of thermalization, what I have to do is to look at a subsystem. So the system will locally relax to a specific ensemble, like in general, you can think of a Gibbs ensemble. And then if you compute the observable, the expectation value in a specific, in a given region, indeed, this will be undistinguishable from the value of that observable computed in a Gibbs ensemble, for instance. So yes, in general, at large time, you can expect that locally the system will thermalize to a Gibbs ensemble. But when we do this study, we look at the reduced density matrix or we compute some observable in a given region. This is what we are doing is ignoring B. Is ignoring no. It's like if we trace over B, we ignore this part and we focus just on a subsystem where the system thermalizes. And this is analogous to perform a measurement in the part B. And so we still ignore all the part of the measurement outcome in B. However, what these two papers have shown is that if we have a system, we let it evolve, then we measure part of the system and we consider the higher moments constructed from these projected ensembles, then these higher moments contain interesting features because at least in generic quantum dynamics, at late time, they tend towards universal distribution. In particular, they tend towards, for instance, R random distributions. under specific constraint, like on being generic quantum dynamics, so without any conservation law. So something like something pretty generic. This was quite interesting, no? Because basically what we have to do, we have a system, we let it evolve, we measure part of the system, and if we construct the higher moments of the post-measurement wave function on the remaining part, we realize the higher moments of a random distribution. This was the main novelty introduced by these papers. And indeed, they dubbed this idea as a deep thermalization, because it's like if we have a constraint not only at the level of expectation value of the observables, but at the level of the state itself, because we find an equality at the level of these higher moments of the density matrix. So it's something more powerful than, deeper than standard quantum thermalization in this sense, that constrains not only expectation value of observables, but higher moments of the density operators. Okay. So this was the idea behind the projected ensembles. A very nice result, especially, or at least as far as I know, only out of equilibrium. And so
I'm not really familiar with these higher moments. Maybe you can provide an example of any physical thing which can be computed using them or something, because
yes. So for instance, something that has been computed is for a state which is like a product state, and then you let it evolve with some random with a random dynamics, like with some circuit that at any time step you apply a random unitary circuit, and then you can compute. Let's say you fix k, say k equal to 2. And this average can be done by using it's called Weingarten formula. So that you can basically perform the average over exploiting the fact that your circuit is random.
Yeah, but my question is what I can use for this ρ2, for example. I have ρ2 now.
I have ρ2, okay, and then I compare ρ2 that I extract from these dynamics to the ρ2 that you would construct for an R random ensemble. If I have an R random ensemble, I can construct, I can compute exactly all these higher moments actually. And then I compute the distance between the ρk that, let's say, I've extracted from my experiment, let's say from my random dynamics, and the exact value of the ρ of k that you get for an R random ensemble. And you prove or you show like how distant they are. So in this case, indeed, they find they called I mean, they find that this distance, of course, decreases as you increase the size of the B part, so the size that you are measuring. In this case, it's really an approximate in the sense that the distance is not exactly 0. No, let's say that it decreases very fast with the size of the system that you are measuring. There are other classes of models which are called dual unitary circuits. That are, it's a class of exactly solvable model where they could prove that this distance is exactly 0 when in the thermodynamic limit. So when this size that you are measuring is infinite. I think the other class of states for which this equality has been proven is for the Kick-Teasing model. So these are, I mean, of course, you cannot prove for, it's hard to prove for a generic state. The idea is that if you have a state that has some, that you can solve exactly and contain some kind of randomness in it, then by doing measurements and so adding a further layer of randomness coming from the measurements, you can create these the higher moments of the R random ensemble.
Just to understand, the higher moments are, for example, used to compute the Rényi entropies.
or
You can
something?
compute, I mean, when you compute the
So
distance,
just more
indeed,
generically, I mean, in a sense, beside the projective ensemble.
yes, indeed, in what I will do, I may
Because
focus on the-
usually, I mean, if you say, if you with the row, you can compute all expectation values. For us, I mean, it's already very good, but you're saying if you have higher moments,
you can,
compute more generic observables that have to do with quantum influence.
yes, you can, if you have higher moments, you can really constrain the distribution of states that you can get. And this will be indistinguishable at the level of the local observable that are linear, no, in that quantity. So you really need to break the linearity in the density matrix.
Why do you use them for any attribute?
No, like,
Isn't it enough to know row one? Is it? And you have to, like, usually you take row to the n, some log, yeah, but.
he's thinking of taking
Yeah, but this is a tensor product, it's not power.
It's not a power.
This is something different, that's why I'm asking. So.
no, but
what
from
is-
here you can compute in principle, you can take the n power of these and see what happens. Like if you
Yeah,
want to
but-
compute something.
But what you just described is that this row K, you can use them as a tool to distinguish distributions, distinguish different ensembles, right?
Yeah, by computing the distance between these and let's say a target distribution where you expect that, to which you expect that this will tend. But how do you compute the distance, no? Like if you take the Frobenius
This I
distance.
understand, I'm just trying to understand the physical meaning of these things. Because for row one, I understand the physical meaning. I can take row one and I compute anything. What I can compute using row K, apart from classifying distributions.
I see. No, as far as I know, computing row K is to constrain the
Okay, I see,
distribution. It's to, I mean, this has been the main motivation for looking at them. Okay, so in this setting, what was the question that we tried to ask with Alexei, or what were the questions that at the beginning we wanted to ask? Is it possible to compute these higher moments in critical theories? Yeah, is it possible so to use them to do this, to repeat this process of measuring part of the system in the ground state of a critical system? And what is the amount of information that we can extract from this ensemble? Now, when we started to think a bit on how to consider this projected ensemble from a field theory setup, the first problem that we found was that in general, if I have a system and I perform a measurement in a given basis, it's hard to understand whether or not I preserve, for instance, the conformal invariance of the system. So this was basically actually the main problem that prevented us from giving a general description or having a general understanding whether this was doable or not. And so we decided to do something slightly different, which is the following. Rather than measuring, performing complete measurement on the part B, we measure an observable, like for instance, the magnetization or the charge, the number of particles. So I perform a measurement of a given observable in the part B. Also, we didn't restrict to the setup in which A and B must be complementary one to each other. So they can be also separated by these two spins. And so what I get once I perform this projection here is the same wave function where I applied the projector in a specific measurement outcome in the part B. And so in this way, I get what we call an observable projected ensemble, where we have a collection of pure states, okay, because this state is still pure, but it's not a tensor product of pure states. Like before we had our post-measurement wave function was a tensor product of the pure state in B and the pure state in A. Now, this state doesn't have a simple tensor product structure. So if I want to focus on the property of the subsystem A, I need to perform a partial trace. Okay, and what were the tools that we try to use? So we didn't look at the higher moments of this quantity, but something more related to the entanglement entropy, which is the following. We studied the measurement-induced entanglement between A and this notation is for the complement of A. So in that picture, basically, it means these two spins there, which is defined as the sum over all the measurement outcome of the Rényi entropy that I get in a specific measurement, for a specific measurement Q. Okay, so I have my state psi, I perform a measurement, and then I construct I compute the Rényi entropy of that post-measurement wave function, and I average over all the measurement outcome. And this is called the measurement-induced entanglement. The idea is that this quantity should capture the entanglement between A and its complementary once you perform this measurement. And the second thing that we try to understand is more related to the amount of information that we can extract about A once we perform the measurement. And maybe it's easy to explain it using Alice and Bob. So if I have Alice who wants to send a message to Bob, and she does it by sending some quantum states, then Bob wants to understand what Alice was what was the original message of Alice. Now, if these two states are not orthogonal, and usually once you perform measurements, the states are not orthogonal, he asks, okay, what is the best measurement that I can do on my system such that I get the maximal amount of information on the message that Alice sent. And this is called accessible information. And an upper bound to the accessible information is defined by Olevo. It's called the Olevo-Kai quantity. And it's defined as the difference between the entanglement entropy of the reduced density matrix rho of A. So here, when I use this one here, it means that I'm taking the limit n going to 1, coming back to the question about the replica trick that you were asking before, minus basically what I call the measurement-induced entanglement also in the limit n going to 1. So basically, we decided to use these two quantities, the measurement-induced entanglement and the Olevo-Kai quantity, in order to characterize the properties of the observable-projected ensembles. Because for us, these were, let's say, the easiest quantity to compute. Okay, so let's see some more specific example in order to show how the computations can be done. Suppose that I want to measure the charge, like the number of particles in my subsystem B. And as I stressed before, once I perform my measurement, this state here is not a tensor product between A and B. So if I'm interested in the properties of A, I don't have a distribution of pure states, but I have a distribution of mixed states. And this is the first main difference with respect to the projected ensembles. So what I have to do, there is the type of the parentheses. What I have to do is study the properties of this ensemble of mixed state, where basically my reduced density matrix in a given charge sector is simply defined by taking my state, this one, and tracing over all the complementary part of A. And properly normalizing it because, yes, because measurement is not a unitary operation. Okay, so how to deal with this object? The trick is very simple. We use the free representation of the projection operator. No, this is just a delta function between QB and the corresponding measurement outcome. We plug these inside this definition of rho A of Q, such that it can be written as here. Okay. And then I want to construct the higher moments of this rho A of Q. So I simply get an n-fold integral and I trace over the remaining part of my system. So I want to compute this object. A very easy case study study case that one can take is the free compact boson, where the charge is just the integral of these vectors, which have scaling dimension 1, 0 for the holomorphic part, 0, 1 for the anti-holomorphic part. So the structure of the charge, this is the charge operator. And we can apply to compute these quantities, we can apply the replica trick that was mentioned before. So if I want to compute the trace of rho AQ to the cube, what I have to do is I consider 3 copies of my system, okay? Then in each of these copy, I have to insert the operator that I'm measuring, so e to the I gamma QB in any of these. And then I join cyclically my surface along the subsystem A. And I join them such that the last sheet is identified with the first one. So this is the Riemann surface with the insertion of these operators here. And the easiest way to compute the partition function on this Riemann surface with this insertion is just to perform a conformal mapping to the complex plane and then evaluate these traces on the complex plane. Okay, so the main difference with respect to standard computation of the entanglement entropy, if you're familiar with that, is that now we are inserting these further operators due to the fact that we perform a measurement on part of the system. So you see that this kind of setup is very, let's say, very field theory friendly in this sense, because we know how to compute correlation functions on a complex plane.
Sorry, gamma 1, gamma 2, gamma 3 are some phase factor.
Are the variable over which we are integrating.
Okay.
Yes, because the trick is that this projector can be written as
I see. Yeah.
and then actually we have 2 of them, but use the cyclicity property of the trace and the fact that rho, the square of the projector is still a projector, so it reduces to just 1 integral.
So this looks like some four-point function.
Exactly, yes. For the compact boson at the end, these are just vertex operators. Yes, exactly. Yes, indeed. For the compact boson, it was very easy to compute this partition function.
But you were saying that the reason you didn't consider the projected ensemble was because it breaks conformal symmetry somehow.
Conformal invariance, yes.
I don't see it because you can still use this trick. There will be some defect lines on.
No, but we don't have this projector, right? Like this is because I'm projecting. I mean, I'm doing a projection of an observable. So you have to think that I'm projecting in all the eigenstates of the charge with a specific measurement outcome. It's not the same as just doing a complete projection in a specific configuration. Like suppose that I have the number of particles, no? I want to measure in the number of particles, and I do this measurement of the charge. I have 4 sites, and I want to know I'm interested in the measurement outcome with 2 particles.
Yeah.
Given 4 particles, there are different states that satisfy these, right?
Yeah.
So I have to project on all the eigenspace associated to these measurement outcomes with the constraint of having just 2 particles.
Mm-hmm.
But in the complete projected ensembles that I was considering before, I can look at just one single configuration. Like you have an exponential number of measurement outcome indeed. So this is very different. I don't know if I stressed it enough.
Thank you.
Okay, so as you said, this integral can be done very easily. It's a Gaussian integral at the end, or better, I mean, it depends exponentially. It has this Gaussian structure for gamma k and gamma L. And we can also compute exactly these matrix elements that depend on the specific geometry that we are choosing. Okay, just a quick comment. This quantity can be also easily computed numerically. Especially what we did was to consider the case in which the free compact boson reduces to a free fermionic field, and by using techniques concerning involving Gaussian states, this quantity can be implemented numerically, and indeed this is what we did here. And the symbols corresponds to the numerical data, and the solid line correspond to our analytical prediction, and you can see that the matching is pretty nice. Okay, so here we are. We have computed this object, which was this Gaussian function of the gammas, and now we have to plug that expression in this integral. It's a Gaussian integral, and we know how to solve this. And if we solve this and we sum overall the measurement outcome, we compute the measurement-induced entanglement. And you see that the measurement-induced entanglement is just given by the total entanglement entropy plus a correction that depends explicitly on this matrix M, which enter here. Okay, so it has a very simple structure, and as a byproduct, we can easily compute also the Olevo-Kai quantity by subtracting the entanglement entropy part, and it takes this form. Now let's look a bit at the form of this matrix element. So here we have plotted basically this Olevo-Kai quantity for different geometries where we fixed the sides of the subsystem A. We have changed the distance between A and B. Here the total system, I mean, thermodynamic limit, so the total system is infinite, and I'm changing the distance between A and B. Here they are close one to each other, distance 5, distance 10. And we plot this quantity as a function of L2, so the sides of the subsystem that you are measuring. This is a log-log plot, so you can see these numbers are very, very small. It means that actually the difference with respect to the total entanglement entropy of the subsystem A without any measurement is very, very small. Like we are doing something super mild by performing this measurement of the charge. And the reason I think it's related to the fact that, again, the measurement outcome that we have scales linearly with the system size, no? Because it's just a charge measurement. And also, we are choosing a very specific observable, like the charge in B, which is not conserved because it's the charge of a subsystem, but still it's related to a quantity which is a conserved quantity. No? The total charge is a conserved quantity for the free compact boson. So we think that these two factors can indeed make this quantity very, very small. Here I've plotted it for 3 different n. And we have some analytical prediction for the case n equal 1, even though like doing the analytic continuation was pretty tricky. So what we did was to use a numerical algorithm to extract the exact analytical continuation, n going to 1, which is represented by these green lines here. And then we performed some limits just to get an estimate of the analytic continuation, which seems to work pretty nicely as the distance increases. And something that I would like to notice is that, as you can see, if the two systems A and B are close one to each other, this Olevokai quantity decreases almost immediately, it decreases. While when they become more separated, it first increases and then it decreases, and there even more. Why? An explanation that we have given to this is the following. So since we have a critical system characterized by algebraic decaying correlation function, we expect that B must be large enough such that, let's say, the information that is encoded in A can propagate through this correlation function to the subsystem B. So this is why we think that when the two subsystems are far apart one from each other, you need larger sides of the subsystem B in order to reach the maximum of this information that you can extract about A. However, after this maximum peak, it will start to decrease. And a possible explanation for this is that it's like if B becomes too large, we are getting too much information about the subsystem A, and this makes even harder to reconstruct the state that we have in A, because we have more information. It's like if we have more parameters than what we actually need to reconstruct the subsystem A. At least this was our, let's say, heuristic interpretation about this behavior. So in one case, the fact that you need, we have this increase at the beginning can be justified by looking at this algebraic decay of correlations, and the fact that then it decreases, it's because if this sample becomes too large, it's even harder to reconstruct the state in A.
D equals 1 here, there is a site in between, or A and B are touching each other when D equals 1?
They are attached basically. It's like one lattice type.
Yeah.
So in all these computations, we need to introduce a cutoff, and we have chosen the cutoff as 1. So we have to perform some regularization of the integrals. Okay, let me give a broader picture of what happens if we project different operators. Of course, the computation becomes more and more involved, so we try to investigate what happens more if an operator is still a Gaussian operator. And so we can easily compute, let's say, this ratio by evaluating correlation function. And this seems exactly the same as before, but if you look at the structure of these Mij terms, actually it's much worse. And the reason is that for the compact boson, the fact that we had a current with the scaling dimension 1 actually simplified a lot the computations, because there was a simplification between the Jacobian of the observable and the Jacobian of the change of variables. Here, the simplification doesn't occur, so we have to study these matrix elements, being careful in regularizing this integral. Now here, something that one can notice is that the divergence of this integral comes from the case in which the two operators are in the same copy. Like if two operators are on different copies, this integral don't diverge. But when the operators lie on the same copy, a divergence emerges. And this is here, this HS means that I'm restricting to a scalar operator, but we also in the paper we consider also some vector fields. Yes, so this is something that let's say helped us noting that the divergent structure just depends on what happens in each single replica. Somehow helped us in trying to extract the most diverging term and do some computations. Okay. Yes, from there we can compute the measurement induced entanglement also in this case. And let me stress that the main difference with respect to the free compact boson is that now we have this different term. That for the free compact boson, this was 0 because Cn was at the same structure. It was exactly NC1, so it didn't. The dependence on n was very easy, so this term was not there. Here we have a further correction, so it means that we are doing something more in our system. We don't have only this correction depending on the matrix M, we also have this further term that we think it's due to the fact that we are choosing for a generic critical system an operator, a scalar field, which is not related in any way to possible symmetries present in the system. So we think that let's say choosing something which is as orthogonal as possible to something completely blindly, like without knowing what are the symmetries of the system, could have a larger impact on what we are doing. And before concluding, I want to show also an idea that we had in order to get rid of these ultraviolet divergences that we find. As I stressed, we realized that the divergent structure just came from what happens in a single copy. And so what can we do? We thought that if, for instance, I compute my rho A of Q, I compute the purity of this state in a specific measurement outcome, and I average over all the measurement outcome, I can insert a phase. No? When I do my average, I also insert a phase. I'm free to do this. And what does implies if I insert a phase? Well, if I write down this sum by exploiting the Fourier representation of the projector that we were using before, basically, if I bring the sum over Q inside, this gives a constraint on gamma. Like gamma 1 plus gamma 2 must be equal to gamma. And so I can solve the integral. And now the divergent structure of this term is encoded in M11 here and here. So I can divide by what happens in one single replica copy with this prefactor for the charge in order to get rid of the UV divergence.
Sorry, I missed it. This divergence comes from which edge of the B region or edge of the A region?
It comes from B.
I see.
It comes from the fact that yeah, it comes basically from this correlation function. I mean, when when I is equal to J, these 2 points coincide, and there we have a divergence. So it means that it doesn't relate different copies, like I and J must be equal, and so it's a divergence that occur at the level of the single copy. Yeah, and we thought that this could be a nice trick if one wants to compute some UV finite quantity. So you insert a phase when you average, if you want to compute the purity, and then you divide, but what's happening in the single copy in order to cancel exactly the divergence. Okay, so it's a good time to summarize what we've been doing together with Alexei. We have introduced a new framework to study projected ensembles more in a field theory setup, what I've called observable projected ensembles. And we were able to look at this, let's say, we were trying to ask the question, okay, what is the change that I'm inducing in my system by measuring in a charge in another part of my full system? And we were able to detect this change by using both this measurement in use entanglement and the Olevokai quantity. Which also have as let's say a more quantum info meaning as an upper bound to the accessible information. We mainly focused on Gaussian theories using the free compact boson as a main study case. And we also try to extract some universal quantities by getting rid of specific divergences. And something that I haven't emphasized so far is that in principle, this protocol can be experimentally also implemented by using a toolbox that is known as randomized measurements, which is a toolbox recently used to compute experimentally, for instance, the Remy entropy and any functional of the reduced density matrix. So since our observable projected ensemble is a functional of the reduced density matrix, and also the statistics that I have to accumulate is much lower than what happens for projected ensembles because it scales polynomial in the system size and not exponentially. We think that something like the measurement in use entanglement could be accessible, let's say, in an experimental setting. Now, what to do next? Okay, first of all, I would like to come back at a certain point at the real problem of projected ensemble in field theory. Try maybe to restrict to a given subset of measurement outcome that don't break conformal invariance or that can still allow for a field theory description of the system. Then some, let's say, basic question that, of course, also given the introduction that I gave about the projected ensemble is natural to ask is what happens if I have a system, I let it evolve, and then rather than doing a complete projective measurement, I measure an observable. No, so the same setup in which I discussed before about the deep thermalization, I can apply in this setting, and I can ask, is there any distribution? Of course, not the random distribution that we saw before, because that was that I think would require an exponential number of measurement outcome, but something different can still emerge by running this kind of protocol. And also something that I was briefly mentioned during the talk, which is still, let's say, an intuition, but I think that it could be properly formalized, is that is there any connection between the observable that we choose and the symmetry of the system that we have? Like, is it true that if the observable is related to the symmetry of the system, is somehow less revealing? It gives a milder contribution, for instance, to the measurement in this entanglement than choosing something which is completely blind to the symmetries that we have. And yes, I think that's all. Thank you.
Are there any questions or comments? I don't know if you know one.
So is there some maybe some simplified setup where you know exactly that you have a family of observables and you know how much entanglement you're gonna get? I don't know, some I don't know, whatever, some toy model maybe where you have you know exactly whether it's gonna maximize or minimize the measurement in this entanglement depending. Maybe it's related to the last question, to the last comment you made.
Yes, so the problem, in principle, we have an expression depending, no, we have this expression in principle, and we can put these integrals on Mathematica and try to solve them. The problem is that there are, we don't do it because there are many parameters involved, it depends on all the parameters of the of like the geometry that we are choosing, mainly the size of the system that we are measuring. It depends on the dependence on the observable just enters through the scaling dimension. So this is good, let's say. Yeah, the main problem is writing this integral that I was writing before in a smart way, such that you can regularize and find the divergence.
Can you please show once again these plots with sky?
Yes.
Yeah. May I ask you to reiterate why? What is an explanation for why these lines go down for larger system size?
Yeah. So the idea is okay. So suppose that this is P, no, and I measure a charge, another charge, another charge, another charge, another charge. At certain point, I measure all of these, and let's say I reach the best configuration where more or less they have the same it has the same size as A, so there is let's say a correspondence 1-to-1. But then it's like if I measure too much, let's say a single point can correspond to several points in B. And so having too much information about B, okay, this B actually is becoming larger and larger, makes it even more difficult to reconstruct the information about A. It's like if you have to solve a system of equations and you have too many variables, and at the end you cannot, you need the one-to-one correspondence, let's say, between A and B. And in this case, we have too much information, and we are not scaling also A, like the size of A is fixed.
Okay.
So we miss this correspondence 1-to-1.
So 1-to-1 doesn't mean L2 equal to big L.
No, they don't have to be exactly equal, but let's say they cannot be exactly equal because this formula is anyway a bit like if you look at exactly if you want to maximize that formula, it's a bit more complicated. But more or less, I mean, this is okay. This is the log. Need to take it into the log.
May it be reformulated a bit in a different language, saying that if I take B too large, I take information from sites which are too far away from A, and they are not correlated very much, and they just add noise into the measurement. As
it's like if you are adding noise, indeed.
Mm.
At least in it's an heuristic picture. Let's say it's nothing rigorous, but yeah, I think more or less it's good.
And so then this size of B should depend on the scaling exponent, I guess, or something, on how fast the correlators decay.
Well, I think so, because now, for instance, this we could approximate, we could compute it in a very approximate way, and it scales as 1/log of the size that we are considering. And I think this log, it's related to the fact that the operator that we are considering as a specific scaling dimension, but then it can, let's say that the explicit form of this indeed depends on M. And yes, I think that it should depend on the scaling dimension of the operator that we are considering.
Can I ask you what's the role of locality? Meaning, like you're selecting a subsystem and you're measuring it, right? And then you're looking at the distribution of what is remaining. But now in this example, you're selecting a subsystem that is like kind of, I mean, you're splitting the system in two and you're looking just 1/2, let's say, right?
No, they're not complementary.
Well, yeah, they're not, but I'm saying like they're not intersecting here, right?
Ah, yes. we are
So
not
if
intersecting.
instead you have a collection of qubits or particles, atoms, whatever you want, now you select some of them, but without separating the system in two. But is it important that like you're doing this?
I mean,
separately?
at the level of the protocol, no.
But at the level of the result?
At the
you
level
just-
of the computation, I think it will become a bit more complicated, no? Because now, when you have to integrate, no, it's like when you have to integrate, this integral becomes split into several regions. So it's like if you have to compute the sum of